It's always a pleasure to talk with students. I've really enjoyed interacting with you guys, and unfortunately I'll be heading out for some travel. So if you want to catch up with me, definitely try to do it today. Okay, so I'm going to talk to you today about the atomic pair distribution function technique. It's called the PDF technique. A little bit about myself. I've been an instrument scientist here for about 3 years, and prior to that, I worked at the Lujan Center in Los Alamos. Has anybody used the Lujan Center prior to its closure in the BES program? No one? Okay. And before that, I had done a postdoc in neutron scattering, and around the time, actually kind of right at the beginning of my PhD work, I attended neutron school in Los Alamos myself. And I just wanted to echo the observations of others that the group of people you meet in a school like this is a group of people you'll see throughout the rest of your career. And so, especially as a beamline scientist, I see a lot of the folks coming in, doing experiments here and at the Synchrotron sources and elsewhere around the world. I have a team of postdocs, actually. We work on an early career research program with BES. And, but today, I'm going to be talking to you about the technique of pair distribution function studies. So you don't have these 2 slides online, but I wanted to kind of get everybody in a good mood, and wanted to share a little joke that I had with my son recently. So Riston is 5 years old, and he says, "Mommy, what do you do at work all day?" I said, "I use neutrons to look inside all kinds of materials so we can understand and improve them." And he says, "Why do you use neutrons?" I'm paraphrasing a little bit, but I said something like, or started to say something like, "Well, for one thing, they can see small details deep inside materials, even really heavy metals," to which he just got shock and awe, because what he thought of was this. "So transformers have a place to go for x-rays when they get hurt?" To which I said, "Well, I guess so." Because I had this picture, which I tweeted to his preschool classroom, and this was Optimus Prime coming in to take one of our caskets off to storage. All right, so all joking aside, what is local structure? When you hear this total scattering local structure technique, we're talking about ways to look at disordered materials, so materials that have defects on a local scale that aren't reflected in their long-range crystallographic structure. We're talking about non-crystalline materials, so amorphous solids, some of you study concretes, polymers, or nanostructures, so materials that have just a well-defined local atomic order, but they don't have long range. And nice review over the different areas where this technique is useful is given by Simon Billinge and Igor Levin, and I encourage you to go look at that. Here's pictographically materials that, so in a porous material, the gas inside the pores is something with local structure, and its interface to that porous material's local structure. A finite nanoparticle, or like point defects in a semiconductor, so it'll all be good examples. And I've borrowed the next few slides from my mentor and colleague, Thomas Proffin. He runs the Neutron Data Analysis and Visualization division here. He's also a total scattering expert. And I really like this simulation for its simplicity and how it demonstrates why you would want to look at diffuse structure in materials. So this is a simple simulation of dark atoms and vacancies. And there are 125,000 unit cells in a 3D volume. This is just one cross-section. And this is a material where, on the left, we have a random arrangement of these vacancies. But on the right, we have some short-range order in those vacancies. So if you look at just the Bragg scattering from this material, so you look at all the HKL reflections possible, they look identical. And this is because in Bragg scattering, you have the information of averages, average positions, average displacement, there aren't any here, and occupancies, which are the same in those 2 pictures. So we can move to powder diffraction. So now we're looking at our data as a function of 2 theta in intensity. And from very far out, the chemical short-range order calculation looks so identical to the random one that they're right on top of each other. You don't see anything at full scale in the difference curve. But if you zoom way in, so the intensity scale just changed here, what you see is a different baseline that these sit on top of. And in this, what we call diffuse scattering signature, you'll find the chemical short-range order. We can take a Fourier transformation of that diffuse and Bragg scattering diffraction simulation and create a pair distribution function from that through a sine Fourier transformation. And that is what an example of what a PDF is. And the difference here, because we're looking just at the local scale, now the difference between these two materials is significant on a scale that you can see. Okay? So another way of thinking about the PDF, it's the probability of finding an atom at a distance r in real space from any other atom. So if we start at the atom in the middle and we start going a distance away, you find the first set of neighbors at 1.42 angstroms and 2.46 and so on. And so it really is an atom by atom histogram of all the pair-pair correlations in material. Now this is a very simple 2D structure. It gets a lot more complicated when you get to complex disordered materials. Another important aspect of this is that there's no requirement of long-range crystallography to produce a PDF. You can equivalently measure all diffracted X-rays or neutrons from a crystalline material like silica or a amorphous material like silica glass, quartz up here, glass down here. You'll see Bragg features and some diffuse scattering beneath it there. You'll see just diffuse broad features there. If we look in real space, you'll see that their local neighboring environments are very similar. They have a difference in their correlation length scale. So this PDF goes to 0, meaning we don't find distinct pair-pair correlations beyond about 10 angstroms in that material, where here they'll keep going and going and going depending on the resolution of my instrument. Okay, so what are the different things we can learn from this function? Well, I just told you about looking at interatomic distances. That's certainly true. If we normalize the function a specific way, areas under these peaks tell us the number of next nearest neighbors. And so a lot of glass and liquids studies, they're directly getting neighbor correlation or, the number of next nearest neighbors from these measurements. And then if you follow it to where it dies out, you'll either get the largest correlated length scale in the material, or you'll get a measure of the finite size. So imagine if you had a nanoparticle. When you reach the largest atom-atom distance in the particle, anything beyond that has intensity 0. So all those things are things we can look at, you can learn from the PDF by just looking. Now, if you do a quantitative analysis of this function, and almost the entirety of the rest of the talk is examples where we've done that, you can, just like Rietveld type analysis or a single crystal type analysis, you can propose a model and do a calculation. So our fit in orange here, our data in black there, and a difference curve falling below. That's a motif you'll see throughout the rest of the work presented, by the way. You can refine things like atomic positions, their displacements, chemical order, composition, the local versus long-range structural motif, or something like a real space group, and like I said, the correlation length scale, quantitatively. And I know you've heard a lot about the complementarity of X-rays and neutrons, so I'm not going to beat you over the head about it, but I just wanted to point out again that a PDF of even A 3-component system has many, many pair correlations on top of each other. So something as simple as the cubic strontium titanate perovskite, you'll have 3 plus 1 over 2 partial structure factors that build up the neutron or the X-ray PDF. And this is a nice pictorial representation of the fact that the neutron and X-ray scattering lengths, so the contribution of these pairs, is very complementary between the two probes. So what you'll see here is, for instance, oxygen is heavily weighted in the neutron PDF and not very heavily weighted in the X-ray PDF. And there's other complementarities through the rest of the combinations. Okay, and when you get to crystallographic structure like this, if you want to interpret anything beyond maybe the first, second, third neighbor, applying a quantitative model is very useful. Okay, so what types of studies can be done with PDF technique? I'm going to go through 4 kind of general overview slides, and then we'll drill into a few specific examples. So the first kind of topic or theme is local distortion via PDF. So these are things like local dipoles in ferroelectrics, so things that exist short range and not over long range. A Jahn-Teller distortion that might persist below a crystallographic phase transition or above a crystallographic phase transition where it appears to disappear. Frustrated lattices, so many condensed matter fields, the Kagame lattice and related things have a lattice frustration that induces a lot of local, unique local environments. And these are examples in that realm, everything from lead chalcogenide materials to pyrochlores and superconducting layered materials. A couple of my favorite examples there. Another, and this goes back to that nice set of simulations from Thomas, chemical short-range ordering via PDF. So this would encompass your substitution effects, chemical clustering in materials, ion-specific local environments, and any kind of vacancy ordering. One of the classic examples is copper 3 gold alloys. So long range, it's a disordered alloy, but at short range, it actually prefers these different local environment symmetries. This is an example of oxygen and nitrogen, so anion short-range ordering in a perovskite material. And this over here is the result of doing what we call a large box model. I'll explain that a little bit more later, to a Jahn-Teller distorted Spinel, where it was seen that when manganese and copper occupy a tetrahedral site, they have very similar bond lengths, and actually in the octahedral site, they have very different local environments. And this helps explain many materials properties. The third area for PDF study is all-encompassing nanostructure, nanomaterial studies. So this could be, for example, silver nanoparticles inside a porous framework. And that's an example from Karina Chapman here. This could be different size and shapes and surface structures of metal oxides. Or it could be a ligand attachment at the surface of an oxide nanoparticle. Specifically, neutron PDF is sensitive to both the light atom species at the surface and the interface versus the heavier atom species at the particle core. So that would include finite size and shape effects, their surface structures, nanostructure polymorphs, and growth and transformation. So you may be familiar that there are a whole zoo of nanomaterials that only, or structure types that only exist at the nanoscale, and this is a way to study those. I should mention that the PDF is a bulk technique. And so to see anything like a surface or interface, it does have to be a significant proportion of all the atom-atom scattering. So for a really large nanoparticle, you wouldn't see much of the interface. When the particle's small and a large proportion of the bonds exist at the surface, that's when you have sensitivity to that. And then the fourth area is amorphous structures via PDF. So this could be a gas or a liquid inside a framework structure. It could be a bulk metallic glass forming. This is a time-dependent crystallization of bulk metallic glass, or an amorphous to crystalline transition in amorphous calcium carbonate. These are all examples. For those of you working on NOMAD this week, I think you are in the lab making some amorphous materials that you're looking at with the levitator that we have out at NOMAD. Pretty neat. So concretes and other amorphous industrial materials would be another category there. Okay, so now I'm going to go through a few examples in a little bit more detail. The first one, I just have 2 slides on this. It's to demonstrate how you can have a different local atomic structure that's consistent with a long-range crystallographic symmetry. Barium titanate is a really nice example of this, the canonical ferroelectric. And if I draw some just cartoon models in 2D, this actually works in 3D in real life. If I think of these at the center of the unit cell, this would be an atom displacing. So this is like a dipole in each unit cell. If all of these dipoles are pointed in the same direction, I can represent this well with one average unit cell. And so this would say I have a polarization vector in that direction. Similarly, if they were all pointed in this direction, I can describe that with a single unit cell. But what about this case? Because in this case, I still have a net polarization in this direction. But this doesn't really describe that true state. And the PDF is the technique that comes alongside crystallography and helps you distinguish this case from this case. And so in barium titanate, you have a rhombohedral ground state, and you have transitions to orthorhombic, tetragonal, and eventually cubic phases. And this is where the polarization vector changes as a function of temperature on average. But locally, it's always the same. So if I was to calculate a PDF from the crystallographic phases of barium titanate, I would see the nearest neighbor pair-pair correlation over here is predicted to be split. So I have 3 long and 3 short titanium oxygen distances at the lowest temperatures. And then you have the average structure prediction says that eventually you have them all not polar, so all the atoms are sitting in the center of the unit cell. But what you find locally is that you always find this splitting. So it's absolutely the cartoon that I showed you before. This near neighbor pair-pair correlation is always fit no matter the temperature with that ground state rhombohedral structure. And at different crystallographic transitions, there's just different directions that are averaged to give you a net polarization vector. Okay. The next example is one that looks into cation ordering and the length scale of that cation ordering. And this is actually a study we have completed at the PowGen instrument here at the Spallation Neutron Source. It's a nice high-resolution pair distribution function machine, part-time. It's usually applied to crystallographic Rietveld refinement, and I think Ashvia is giving you a talk. She may even discuss this example. So the high-voltage Spinel cathode, LNMO, This material has a very high operating voltage and really good lithium ionic conductivity. And it's been known for a long time, for a while, that there are two distinct polymorphs of this material. One where the cations are fully ordered, and another where you have some partial sharing of one of the sites by manganese and nickel. There's a space group, a higher symmetry space group where nickel and manganese are randomly distributed. And then there's this ordered phase, which is represented here, where you get ordered nickel and manganese. And these are made by different heat treatments, basically, during synthesis. And interestingly, this disordered one functions a bit better as a high voltage cathode, and the mechanisms are really not very well understood. Part of the reasons are that the exact structure of this thing is debated. So Ashvia and colleagues had done a nice Rietveld study of this material. As you go from the disordered state to the ordered state, you see the appearance of reflections for cation ordering. And so this can be refined as a cation occupancy. And so on average, the average cation ordering of those materials at least partly distinguished why some of them performed a lot better as battery cathodes. Okay, so we have SC-FC. These are slow-cooled and fast-cooled spinels. And then we have ones that have been annealed, and that's when you see the A here, one for 48 hours and one for 240 hours. Actually, these two looked extremely similar by diffraction, and in the paper, they actually only show one of them. And then there's a small increase in ordering when you go from 48 to 240 hours. Okay. One thing to note here is that there is a very large nuclear scattering length contrast between nickel and manganese. So this is a great opportunity for looking at cation ordering with neutrons. And here you see that you can tell a lot by just looking at a pair distribution function, as I mentioned earlier. So if I draw the lattice here of just the manganese and nickel on one plane of this material, I can draw 2.86 and 2.91 angstrom distances, 8.7 here, 5.73. I can just tell by eye that locally, actually, all four of these materials have identical local structure. It's when I go to the third and fourth cation neighbors, I start seeing a difference. And farther out, they're starting to look pretty different. So now we can go, and I'm kind of stepping you through the stages of a real space analysis that you might be able to mimic in your own work. Now you would go and try to model that local versus long-range structure by proposing different models. And so if I use the long-range determined structure for those fast-cooled and slow-cooled non-annealed samples, I find that the long-range average structure fits these materials really well at higher length scales and not at all locally. I fit the whole range well using the ordered cation model there. Since we looked at them on top of each other, we already know the answer, that we need to apply this model to this region of these materials. So this is a strength of pair distribution function studies, where you can not only identify the nature of the local structure, but also its length scale. How long does it persist in the materials? This is often what will govern their, in this case, lithium transport or conductivity properties. Okay, so we can now, looking at the fast-cooled and slow-cooled models where I know the average structure is no good locally, I can apply that cation-ordered model. And if I do that as a function of real space, so I take that model and I'll apply it across the whole real space range, I'm refining the occupancies as I go. What you see really clearly is that over 50 angstroms, this annealed samples are fully ordered. That's no surprise. But these fully disordered models don't become so until about 15 angstroms. And what was really interesting, I haven't shown it here, but if you go even farther out to say 150 angstroms in real space, these materials actually begin to look different. So, and it's this length scale for that cation ordering that links really well to observed properties. Okay, so that's called actually a boxcar refinement when you apply one crystallographic model over different lengths of real space and see what changes as you do that. The other example I'll go into with some detail is not one of my own. This was done by my colleague Shouwen Wang. She actually is a scientist here at Oak Ridge. And she works in the geochemistry group. They do a lot of studying of different oxide metals and nanocrystals in the environment and weathering. And they had a lot of interest in understanding the stability of different crystallographic materials and nanocrystals in the environment. And they noted that very small tin oxide nanocrystals, when you put them in thermogravimetric analysis, have two steps of dehydration. So it suggested that there might be several types of water or something else existing at the surface of these particles. And so they want to know how many layers of water are there, how is it bonded to surfaces, and what are the dynamics of dehydration. They're intimately linked to the growth and stability of these materials. So, at least in Tennessee, when you have tin oxide sitting out, it does absorb a lot of water to the surface. And when you measure this material in our dedicated total scattering beamline NOMAD, which is the highest flux neutron total scattering instrument in the world, you see something really interesting. So these materials were made in a deuterium environment, and so they have heavy water at the surface so that we can study them well with neutrons. But you'll see this DO correlation here at room temperature. And then they did this dehydration in situ, and you can see the water coming off. At the point that it all goes, this material actually starts to grow. So you can see by eye again a lot of really interesting physics of this system. And they actually went very far in their analysis and interpretation. They do a lot of molecular dynamics and other theoretical work in their group. They compared their measured data to MD simulations. So this here is water and hydroxyls jiggling around the interface of tin oxide in this case. And they compared more than two, but the highlights of two models are here. One where they had hydroxylated interfaces and one where they had non-hydroxylated interfaces. And they could see that the hydroxylated model was the correct one for the system that they measured. And then they were able to track, as a function of dehydration, how many layers and what type of water are present when. And then fit their data with a crystallographic model for the tin oxide, plus their MD water layer structure. This is one of the series of data we've actually provided in the NOMAD tutorial for those of you doing that hands-on activity this week. So in the end, they could combine their results from PDF, which was sensitive to the tin oxide internal metal oxide structure, plus the hydroxyl and water species at the surface, and learn a whole bunch more than anyone ever knew about surface-bound water species and how they affect stability and growth. It's a great paper if you have time to go look at it. Okay, we have a few experimental considerations of the PDF that we definitely want to cover. Before I go on, is there any questions about any of those examples? Okay. The total scattering structure function, I wanted to say a bit about how it is experimentally determined or measured. It is basically the measured differential cross-section with appropriate corrections. So we correct it for container and background scattering and self-absorption of the container and the sample. We normalize by the incident flux, number of atoms, and square of the scattering length or form factor X-rays. There's a nice detailed derivation and relationship of this function to other forms in these two papers here, if you want more detail than that. So recall that the scattering length for neutrons, the atomic form factor for X-rays is actually Q-dependent. So the function is a little more complicated when it comes to X-rays, but it's closely related. Okay, so we do all those corrections. And by the way, it's really important to measure the background carefully. When you're looking for diffuse scattering, it's typically a very small signal in the presence of Bragg scattering. So you really need to know very well what's the scattering from your sample and what's scattering from everything else in the environment. So, all right, so this function is the sine Fourier transform of this total scattering, and by total we mean Bragg and diffuse. And if you look at the equation for the PDF as a function of Q, you can see that it is integrated between a Q min and a Q max. Now, theoretically, this would be from 0 to infinity, but we can't measure from 0 to infinity. So those are also experimental artifacts or features that we need to take care of when we apply this method. So to obtain a very high quality PDF, you need a high Q maximum. It's related to that relationship I just pointed out. You also need good Q resolution. I'll show you directly the impact of higher, lower DQs in a minute. Very good counting statistics, especially at that high Q range, and a low and stable instrument background for the things I just told you about. An ideal instrument would have no contribution from instrument resolution, of course. And in PDF, we often have a balance of wide Q range and high flux with resolution. And so these are often medium resolution diffractometers in facilities and not the high resolution diffractometers, because we're trading intensity and Q range for resolution. Okay? So those conditions are met at high energy synchrotron sources and at spallation neutron sources like you're visiting today. Okay, so the next two animated slides are ones borrowed from my colleague Phil Chater at the Diamond Light Source in the UK. It's a very nice visualization of this. So the reciprocal space, or the peak width, the Q resolution effect, ends up determining the dampening function in real space. So when you have nice high Q resolution, like you see here, you get a PDF that extends out to high R. And don't worry that this is called D of R and not G of R. When you cross the ocean, you have to change what you call the function. So, all right, as this starts broadening out, you'll see that this function dampens more sharply, and so on and so on. So the intrinsic peak resolution you see at the amorphous area detector synchrotron PDF beam lines is much closer to this. And the resolution you find at our instruments here, Nomad or PowGen, is much closer to the high resolution there. So we have access to much higher real space ranges. That's a real strength of neutron total scattering studies. Of course, it's a lot slower. So, okay. The other one to discuss is the maximum Q effect. You do have two effects. There's one that's just the Fourier termination you get with specific Q maximums by terminating the function. And that's just a simple sinc function convolution with all the PDF peaks. But the one I want to cover in more detail is this delta R resolution effect that's dominated by Qmax. So an example, simulated example here for aluminum phosphate or ALPO, where there is quite distinct pair-pair bonding between phosphor and oxygen versus aluminum and oxygen. So we should have a split first peak. That's the real structure. If you measure this on a lab source, you can actually measure PDFs in your lab. They're just very low resolution PDFs, and you have to count a long, long time. You don't distinguish those pair-pair correlations. You can do better with a molybdenum source, and the PDF lab instruments in most universities are molybdenum or silver. They're mostly molybdenum because the silver fluorescence is kind of tough to deal with. You can maybe start seeing some peak asymmetry if you can go out to a Q maximum of 22 inverse angstroms. This is actually the maximum Q of a lot of those amorphous area detector setups I told you about. If you want to distinguish these peaks, you can start to do that at Q maxes of 25 and higher. At 30, you definitely can. And at 35, and this is well within the reach of the Q range we have on the Nomad and PowGen instruments, you can really distinguish this local atomic structure. So that's an important experimental factor to keep in mind. Okay, so the instruments at the SNS that we have to do this type of measurement or tie this type of measurement include our dedicated Nomad, nanoscale order materials diffractometer, beamline 1B. To a less extent, the spallation, neutrons, and pressure diffractometer is SNAP. So SNAP is the high pressure beamline. A lot of times we do look at a total scattering structure factor at SNAP because of this effect of the low Q max. We don't often transform it to look at real space, but you can do a low resolution PDF of like novel pressure phases there. The other one is the powder diffractometer PowGen. I know Ashley will tell you a lot more about that. It's recently been upgraded. We used to have to collect PDF data there in 2 different frames of the instrument and merge them. And with its new detector upgrades, we can actually, in one measurement, get a decent pair distribution function from that material. And you kind of have a higher flux, lower resolution, still high flux, medium resolution, and lower flux, high resolution options in the facility. To give you a comparison of at least these 2 instruments where this is more frequently done, you can see this result I was telling you by eye. See the intensity is persisting to higher R here in the PowGen, higher resolution PowGen data than it is here up at Nomad. And so the typical data collection is about 100 milligrams in 1 to 3 hours at Nomad. Faster or slower depending on how good of a scatter it is and how crystalline the material is, et cetera. How much material might absorb. At PowGen, you're talking about a much bigger sample, so something at least the size of your pinky, say, 10 grams or so of sample in a 6 to 10 millimeter vanadium can and measuring from 8 to 12 hours. I would say that's probably cut in half now that they've had their upgrade. And we've measured, very recently done new measurements on the upgraded PowGen. We just don't have the results ready to share yet. But you can think about this as for high intensity and doing anything time resolved, And also for amorphous and nanostructured materials, you would go to Nomad. And if you want a detailed crystallographic analysis of your crystalline material that has a little bit of disorder, you might want to go to PowGen. I want to say a little bit about the most common total scattering technique at the synchrotron sources these days. And one of the biggest reasons is they're super fast. So in something that takes us minutes to hours, they're doing it in tenths of a second or a second. Their flux is just incredibly high. And the most popular mode of PDF collection these days is on these 2D detectors. So you get a diffraction pattern here, and you integrate around the ring, and you get a total scattering structure function. Same way, subtracting the background and making corrections. Create a PDF. The difference is that this is for a crystalline material. You see it's damping out very quickly. So you can study local atomic structure with great fidelity at these beam lines. But if you want to look at, like we did with that lithium Spinel material, if you wanted to look at the intermediate range structure, you wouldn't be able to do that there. So the great application, I think, of these techniques is time resolved and as a function of temperature, pressure, et cetera. Okay. Spend a little bit of time talking about how you model a PDF. As a reminder, this is very similar to the graphene material that you saw earlier. This is a 2D reminder of what we're doing. We're counting the atom-atom pairs from each atom in our material and adding them all up together. So that's a pretty simple thing to do. It's actually quite easy to calculate a PDF. You find all the distances between atoms I and J. So this is a delta function here. So I have intensity at each distance between atoms. And then I weight that by the atomic form factors or scattering lengths for neutrons. And I add all those up. I subtract an average density. And then I can compare a calculated PDF to a measured one. In a few more steps, if you do what I just said, you'd get a function that looks like that. Okay? You have a delta function at all the distances as a function, and you know how many of each number you have because you're dividing by the average. What you need to do, there's two different approaches. And there's variance in those two different approaches. But in general, you can break them up to, in a small box modeling program, what you would do is you would take these and convolute them with some description of the peak width. And that description would include some crystallographic parameters and some instrument parameters. For a large box model approach, I just rely on a statistical distribution of my atom-atom pairs to make up the widths of the peak. So you have to make the box big enough that it wiggles around to fit all those pair-pair correlation widths. That's what kind of distinguishes the two approach. But they're all using this basic calculation to get there. And then you can add the different instrument effects so that you can truly compare this PDF to what you've just measured. And there are quite a few different software suites for doing this. The small box ones, most popular are PDF GUI. That was written by the Billinge group. The newest version of Topaz has a small box PDF calculator in it. So here, this is that real space Rietveld type approach. So this is, again, the one where I count up all the distances, and then I do a convolution based on atomic displacement and peak broadening instrument effects. The large, and 20,000 atoms is probably smaller than is, you can do bigger these days, actually. But typically, at least 20,000 atoms in a large box. And you can fit the same model to X-ray and neutron diffraction, to PDF, and to Bragg profile constraints if you want. This gives you a static 3D model, or like a snapshot of the structure, and you'd have to do like many of those and average your statistics to get meaningful results. There's what we call multi-level or complex modeling available, and so examples of that are what you can do in the Discus and diffev programs, they're called. And this is where you say, I know in plane the crystallographic, this layered structure in plane, in the AV plane, is well ordered. So I have a motif that I fit to my local structure based on that. But then the longer range interactions may be governed by, say, turbostratic stacking, something like that. Then you can include higher level parameters. So it's kind of something in between these two approaches. And then I showed you one example of MD compared to experimental PDFs. That's definitely still an emerging area. I would say it's becoming more and more popular. You can always give your PDF to your favorite theorist and see what they can do with it. So, and a little bit more about the pros and cons of the different software programs available today. And I would encourage you, if you're interested in this area, they're actually pretty fun just to play around with, and you can simulate patterns. You don't have to have experimental data to try these out. The PDF GUI program is open source and it's free. It has a graphical user interface that's simple, so it's not as flexible, but it's very easy to use. And in fact, in the Nomad tutorial, in about an hour, we kind of show you most of the features of the program. So it is, however, pretty slow, especially for high real space ranges. And that has to do with the kernel of the calculation, how they're actually doing it. The Topaz PDF program is very fast. You have to write your own macro, which is both good and bad. It can be complicated or intimidating to get started, maybe, but that means that you can do really interesting things with the modeling. So you can, in this program, fit both the Bragg scattering and PDF together. We just did a week-long school, which some of you came to, on uses of this software, and we spent like a day and a half on the new total scattering capabilities in there. I'll just say a little bit about reverse Monte Carlo modeling. Actually, we're fortunate here at the Spallation Neutron Source. One of the main developers is my group leader, Matt Tucker. I guess I didn't point him out on my first slide, but if you go back, you'll see that. And so we have quite some active development of RMC profile happening here now at the Spallation Neutron Source and in the US. Anyway, this is, I already talked about a lot of this. One of the key points about applying the RMC profile approach to PDF data is that the use of constraints is very important. RMC will fit everything in your data. It'll fit all the artifacts as well as the real pair-pair correlations from your material. So it's really important to get high quality data when you're doing this. And then it's also really important to consider what you know from your vast knowledge of chemistry or physics. If you know that there's a closest approach of 2 atoms, then you should set a closest approach. If you know that the valency of one of the ions from another technique, you should set it. And actually, some of the newer developments, I think being led by Igor Levin at NIST, are in incorporating things like XAFs and even now electron microscopy into this software. And so they're really going towards a workbench style approach where you can, with one large atomistic model, fit all kinds of different experimental inputs. Okay, and then with a few minutes left, I'll discuss some emerging areas in total scattering techniques. So I don't know if you've ever thought about it, but with neutrons, we also are sensitive to spin-spin interactions. And those can be local. and not long range, especially in frustrated materials. And so Ben Franston in Simon Villenge's group spent a lot of his PhD in the last few years following up on some work that Matt and Andrew and David and Martin Dunn had done with the reciprocal space total scattering structure functions in figuring out what the math associated with magnetic PDF scattering is. And so there's a whole bunch of papers you can follow up here if you're interested in that. But it's being developed to provide direct access to short-range magnetic interactions and should be of interest to quite a few materials. We're still, I guess, figuring out the best experimental conditions to do that. We don't have a beamline built per se for it, but these earlier pieces of work were done on existing instruments, Nomad being one of them. So another cool area, Teddy Marie is actually a postdoc working with me now, but in her PhD work with Jacob Jones at North Carolina State University, they had looked into doing field-dependent pair distribution function studies. So applying a field and actually, breaking this requirement of powder diffraction that you have isotropic scattering everywhere, looking at the local effects of applying field. And anyway, there's this paper, and now there's several others from that group exploring that idea. Another one that I didn't make a slide for, but I can mention since I have a few more minutes, is what we call dynamic PDF studies. So if you go to one of the spectrometers here, and this work has been done on ARCS, and it had been done on the Pharos instrument at the Lujan Center prior to that, you can get a PDF as a function of energy. Now, one of the challenges there, it comes back to this Qmax effect that I took time to show you, and the resolution effect, because the balance of resolution and flux was chosen on the flux side for our spectrometer suite. You don't get really high real space resolution PDFs from dynamic PDF yet, but this is an emerging field. And so the idea is that as a function of energy, you would be able to distinguish what was static versus dynamic distortions, local distortions in materials with that approach. So that's an interesting area to watch evolve in the next few years. Okay, and before I go to some conclusions, I just thought it was for this audience where you maybe have never heard of this technique or thought of this technique, although it is becoming more and more prevalent in the scientific communities these days. You may be asking, well, when is it right for me to try that technique out? I would say if you've modeled everything you can in reciprocal space, I guess I should preface that with, if you have a disordered material or nanostructure material, you should do PDF. That's the way you can look at the atomic structure. For a crystal material, it's a little more nuanced. When do you know that PDF's appropriate? You start out by modeling everything you can with the Bragg scattering type approaches. And then if you have some unexplained structure property relationship, or you suspect that local structure might explain some difference in mirrored materials, you should go do PDF. And different things that might suggest this of, there's complementary methods like NMR, other spectroscopies. The average structure fails to explain properties. Maybe the theorists that you work with or the theory work that you do shows a different ground state than you observe at low temperatures, those kind of things. And maybe it's because you have lots of experience with a materials family or structural archetype. So if you know that you have a frustrated lattice somewhere, it would make sense to go do a local structure study. And I've provided for you, I won't read through this for sure, bunch of resources and programs you can look at to find more, and suggested a few references and reviews. If you're looking for a really nice entry level one chapter of this field, I recommend the last chapter in this book. it's actually a really easy to read and approachable introduction to the method. And then if you want to know a lot more, you would go to one of these other references. And the bottom one here, this is a book that Thomas Proffen wrote with Reinhard Nader. It actually goes through how you build up a defect model. So how do you make a 3D model that has some, the simulation that we started with, that was made in Discus. And many more complicated models can be made there, so quite easily with that software. Okay, so in conclusion, or in summary, I hope I've shown you that atomic pair distribution function studies, which I'll remind you mean I have a real space pattern that includes Bragg and diffuse scattering components. It gives you access to the structure of amorphous and nanostructured materials, into how your long-range structure departs from your local structure. And that can be specific to displacements, chemical short-range order, vacancies. There's many other to list there. But not only the presence of those, but what their length scale in a material is, or what the size of the local structure is. So all these things are very key in determining structure-property relationships, which is why the technique is becoming mainstream. And as a reminder, that use of multiple data sets and theoretical inputs always advisable when you're looking at complex materials. And also, high-resolution instruments can specifically tell you a lot more in this complex materials arena. So with that, I'll take any questions you might have.
Any questions right now, or we can corner Kate during lunch?
Yeah, lunch. Yeah. Mm-hmm.
You mentioned calculate the coordination number based on the area of the
Mm-hmm.
elaborate a little bit how to do that?
So a close relative to the PDF is the number. There's a n with an r in it, a number function. So because we measure so carefully the background, and we typically know the composition of a material, if we've made it in the lab, know the chemistry, you can absolutely normalize the function. And because it is all the near neighbor pairs, and that peak is weighted by the numbers contributing to the height, it mathematically completely gives you the area, completely gives you the number of the nearest neighbors. And so you can see if maybe on average you have both 3 and 4 coordinate cations in an oxide, say, but you don't know how many of each you have, then this counting technique would give you that.
So is the background just a straight line?
When you do the number density, the background becomes flat. So you have to know the composition, you have to know the volume, you have to know the packing fraction, and you have to know the density. And if you know all of those things, then you can normalize the function so the baseline is flat and then the area under the peak. So it's just a different normalization of the G of R. Yep. It's pretty typically done in the glass and liquids community.